Okay, let's talk a little bit about probability today and just get into the basics of it, the key axioms of probability or rules, whatever you want to call them, and get to the PPV, positive predictive value, also known as Bayes' theorem. So that's what we're going to do today. So let's just start with a couple definitions. These should be refreshers for everybody. So we're going to talk about random variables and divide them into discrete and continuous. If you think about it, they're random because any variable is random. If you select somebody out of the population, you're doing so at random. So one can have any value on any one of these variables. So if you're looking at a person's biological sex, you could have a male or a female. You're picking people out of the population at random. That's what a random variable is. Now, of course, you're not always going to be picking people at random, but because you could have a specific, say you're conducting a study and you have people entering your study in a non-random fashion. I mean, that's different, but in general, we will assume that the selection of an individual from a population is at random. When we're dealing with discrete variables, those are a countable set of possible outcomes, like the number of disease cases in a SRS sense for simple random sample. So now you know why we talk about randomization from a population. Although a random sample, when you go to a simple random sample, we're selecting people actually at random. In that case, where everybody has an equal chance of being selected into your sample. So, for instance, number of disease cases, so it's countable, and it can go to infinity, right? You could count the number of individuals with coronavirus, for example. So it can technically go to infinity, or theoretically. A continuous random variable, though, is an unbroken continuum. So something like, for instance, the weight of newborns. So you can, if you have two weights between, like, say 7 and 8 pounds, you could have an infinite number of values there. Population is a set of all possible values for a random variable, so we'll call this a sample space here. It's easier when your sample space is, say, just males and females, because we only have two possible outcomes. The event is an outcome of interest or the outcome of an experiment. So if you're selecting an individual, that's actually an experiment. You think about it, if I'm collecting data on people's levels of depressive symptoms, if I'm selecting somebody from a population, that's a random experiment. Probability is the proportion of times an event is expected to occur in the population, and we'll be doing a lot of that now, so you don't have to worry about those definitions, because we'll actually be, well, you do want to remember them, but we're going to practice them as well. Some properties of probabilities. First property is that, and this is, a lot of these, if you just remember these, you're going to be in pretty good shape. You know, a probability can never be below 0, and it cannot be above 1. So if you ever calculate a probability, it's above 1 or it's negative, something went wrong. Second property is the probabilities of a sample space of all mutually exclusive outcomes or events must sum to 1. What I mean by mutually exclusive means that they cannot co-occur. For instance, if you flip a coin, you can get a heads or a tails. You can't get both a heads and a tails. If the probability of a heads is 0.5 and the probability of a tails is 0.5, 0.5 plus 0.5 equals 1. So they cannot co-occur together. That's what I mean by mutually exclusive. I may also use the term complement, because complement is synonymous with mutual exclusive, so are disjoint events. Disjoint, that's another way to say mutually exclusive. So for instance, here we have, so this is the number of successes, and each of these bars represents the probability of success. So for 0 successes, you have this very low probability, 1, 2, 3. 3 seems to be the highest number of successes, the highest probability of success. Has the highest probability. 3 successes has the highest probability. It's 0.4219. So these are all disjoint events because you can't have 3 successes and 2 successes at the same time. So that we can add these together and they'll equal 1. And that's what I mean by this. the sum of all possible events in a sample space must equal 1. So those are each possible event. You have the event of 0 successes, 1 success, 2 success, 3, or 4 successes. By the way, when I say or, that's equivalent to addition. Property 3, the complement of an event is an event not happening. So we use this A with a line over it, so that means not A. So if you have A, its complement is not A. So if you flip a coin to get a heads, a tails is a not heads, right? So that's the complement, and complements don't have to just be one possible outcome. Like here, for instance, the complement of getting 4 successes is 0 to 3 successes. So we know that the probability of a complement is 1 minus the probability of A. The probability of the complement is 1 minus the probability of A. So the probability in this case, so A with a line over it or bar over it is not A. So the probability of not A is 1 minus the probability of A. So if we go to figure 5.1, which is this figure up here, or it's table 5.1, figure whatever. You know what I'm talking about, right? Okay, so what's the probability of 0 to 3 successes? You say, why is he doing this under complement? Shouldn't you say, like, what's the probability of 4 successes? Well, here's why I'm doing this. So we know that the probability of 0 to 3 successes would be this probability plus this probability plus this probability plus that probability, right? So I could take my time and add those 4 together. Add those 4 values together, right? Or if I'm smarter and I like less work, we know that's the probability of 0 to 3 successes is the complement of 4 successes. I could just take this probability 0.3164 and subtract it from 1, which is what I did here. So 1 minus the probability of 4 successes is equal to 0.6836. So I just saved a lot of work. Knowing this idea of complements is very, very helpful. So you should be able to, you can verify this, you need to practice this, and you should be able to replicate this. The probabilities of disjoint, so disjoint now we know means complementary, mutually exclusive events can be added. Probability, so for instance, if I want to know, well, here's the definition actually. If A, and I'll show you the symbol here. If A and B are 2 disjoint events, so this symbol here is the union of 2 events. This is like saying A or B. So the probability of A union B, or this is the same as saying the probability of A or B occurring is equal to the probability of A plus the probability of B. As long as they're disjoint, it means they're not co-occurring, and you'll see why later. So based on the results presented in Table 5.1, so there I did it right, Table 5.1, Figure 5.2, what is the probability of observing 3 or, so you see I say or, that or is really important here, or 4 successes. So either of those 2 occurring. So I'm asking for the union of the 2. So this is the probability of the union of 3 successes and 4 successes, right? So this is like saying, what's the probability of 3 successes or 4 successes? Well, since they're disjoint, they cannot co-occur, we can add them together. So it's 0.4219 plus 0.3164 is 0.7383. So that's the probability that you get either of those 2. That's why it's probably better when you're betting to bet on an either or scenario rather than an and scenario. So those 4 key properties of probabilities, axioms, rules, whatever you want to call them, you need to know those. Always. And they'll save your life one day. So let's talk about expectations. Means and variance, so these are expected values. So the expected value of any sample space is calculated as follows. So this symbol mu stands for the mean, is equal to the, so that I have here probability x equals x. So x is the variable, and little x could be any one of the specific values. This is known as the probability mass function when we're dealing with a discrete random variable. We calculate the mean, or the expected value, by summing the product of each value times its probability. So that's what it means here. This symbol sigma is just the sum, right? So this is the probability. The expected value of this distribution is the sum of each value times the probability of that value. And we get the probability of that value through what's known as the probability mass function. So let's look at this. So we have this distribution here that has a very specific probability mass function. This is the one that we saw in the table above, in the figure, whatever you want to call it. So I rewrote the probability mass function here. Probability of 0 is 0.0039. This is the number of successes. Probability of 4 successes is 3164. If we multiply, as the equation states, if we multiply the value times its probability, so this is the value, here is 0 times its probability. It's just anything multiplied by 0 is 0. Anything multiplied by 1 is itself. That's an identity. And you go on and on and on. So we got all of these elements for this equation here, and we add them because we're told to sum, so we add them up and we get 3. So the expected value of this distribution is 3, of this random variable is 3, right? You'll notice that it also has the highest probability, so it kind of makes sense. Okay? To calculate the variance, so this is the way we actually do things. You think about the equations that, for instance, when we're dealing with descriptive statistics, when you think there's an equation for variance, well, this is where we get them from. Either here, or we could do something called a moment generating function, which is a little bit beyond the scope of this course, but this is another way to do it. The variance, sigma squared is the symbol for the variance, population variance. It's x minus the mean, so it's each value minus the mean squared. So instead of just x times the probability, we're doing this sum of square differences right here. X minus mean squared times the probability. We'll do that for each case, just like we did when we calculated the mean. So the probability, well, we need each element here. So there's 1, 2, 3, 4, 5 different elements in this sample space, or events in the sample space. So let's go ahead and do the calculation. For each one, we have to take x minus the mean. So for instance, 0 minus x minus the mean squared. So 0 minus 3 is negative 3. We know the mean was 3, right? And square, that would be 9, right? So we're going to keep on doing this over and over again. So this will be that element right here, and its product. This is a product again. We do that for each one of these values. Obviously here, it's since this event is 3, x equals 3 here. 3 minus 3 is 0, so that's why we have 0. So this one is 0. This element of this summation is 0, so we get our variance is 0.75. So you need to know how to do this. This is always going to give you the mean and the variance, always, for any distribution. When let's talk about about the area under the curve. We'll be using this, especially when we're dealing with continuous random variables. The area under the curve is just the height times the width. So for instance, when we're dealing with these discrete values, we have the width in all of these is just 1 unit. So these are just bars, 1 unit. And the height is going to be the probability. So this is the number of successes we had in the last example. There were 2 successes. Their probability was 0.2109. 0.2109 times 1 is 0.2109. So that's the area under the curve here. And if we add up all the areas under the curve, we will get 1. So this is something that we already know how to do. We can also calculate something called a cumulative probability. And in fact, when you're in SPSS or in any kind of statistical computer package and you calculate you do a frequency distribution, you'll get the cumulative probability. It's one of the outputs that you end up getting. So it's just adding everything that's to the left in the distribution or below whatever value you're interested in. So for instance, the probability of x is less than or equal to 2 successes is the probability of 0 successes plus the probability of 1 success plus the probability of 2 successes. And again, I'm using that last example we had is 0.2617. When we're dealing with continuous random variables, the area under the curve is very, very important because there are no discrete values in a continuous distribution, or there are, but their probabilities are 0. So like for instance, if you weighed somebody and like me, say I weighed 166 or something, 66.03114795, on and on and on, probability of that value in the population is 0. It's so tiny, so minute, right? Such a very specific value. When we deal with that, instead of calculating the probability of any one specific point, we calculate the probability of some area between any 2 points. It makes it a little easier for us. Here's an example of what we call a uniform distribution. So this distribution has the same value across all points, and the probability between A and B, probability between values A and B, whatever they may be, is 1 divided by this difference, B minus A. That's its probability, and that probability is constant, right, between A and B. Anything below A is 0. Anything above A is 1, because we know that probabilities have to sum up to 1. For this whole area here. So let's calculate the expected value. So this is when we're dealing with, this is a continuous function. When we're dealing with continuous functions, some people might call these quantitative as well. When we're dealing with continuous variables, I should say, well, function and a variable are the same. So when somebody's dealing with a continuous variable, like this one, instead of having a probability mass function, we have a probability density function. However, calculating the expected value is essentially the same, except for now instead of summing, we're going to integrate over the area. You don't have to understand calculus here. If you do, that's awesome. If not, not a big deal here. But we're doing essentially the same thing. We're multiplying the value times the probability density function. When we're dealing with a discrete variable, it was the value times the probability mass function. And then this is our outcome here. Again, you don't have to understand calculus. The average then, or the expected value, is B minus A divided by 2. So that makes sense, right? It's a difference divided by 2, right? To calculate the variance, we can also use we don't have to do the same equation as we used before. We know that there's a shortcut equation for the variance. We could simplify our lives. Instead of expected value of x minus mu squared, we can use this equation because this one allows us to use an item we already have, which is mu squared. So our expected value is the mean mu, and we have it right here, b minus a divided by 2. So we can eliminate this and make our lives a lot simpler doing the expected value of x squared. So that's x squared times, again, the probability density function. We integrate it, and once we're done, we subtract. As you can see here, this is the expected value of x squared. We subtract the mean squared from it, and we get b minus a squared over 2. Again, you could work this out if you want mathematically, but that's not the point of this course. The point is that we have ways of finding the mean and variance of these different probability distribution functions. So I say probability distribution function to contain both the probability density function, which is for continuous variables, and the probability mass function, that is for discrete variables. Well, let's look at some other rules for probabilities. One is the addition rule. We did an addition already where we added 2 mutually exclusive events, right? And it was just a probability. So if I said calculate the probability of A or B, or I think in our case I use a union here. I said, what's the probability of A or B? And I said, it's the probability A plus the probability of B, but you didn't see this piece right here. This occurs when our events are not disjoint, when they can co-occur, or they're not independent. So they can co-occur in this case. So there's some overlap. When there's overlap, and this is a Venn diagram, and the Venn diagram is very useful in understanding probabilities. So you see that there is some overlap between the two, represented by this little footballish shape here. If you think about what we calculated before, if we do the probability of A and then the probability of B, we're going to double count this space. It's already counted in the probability of A, so I don't need to count it again in the probability of B. So I subtract one of those overlaps here. This is the probability of A and B occurring, or its intersection. Here's a pet example from your textbook, but it's all you need is right here. Let's say the probability of cat ownership, and let cat ownership be A, is 0.35. The probability of dog ownership, let dog ownership be the letter B. This probability B is 0.30. So the question is, what is the probability of cat and dog ownership? Oh, I'm sorry, no, that's not the question. I should say the probability of cat and dog ownership is 0.15. That means in 15% of the cases, individuals own both a dog and a cat. In 35% of the cases, individuals own a cat. 30% of the cases, they own a dog. So there is some overlap, like 15% of the cases. Question is, what's the probability that one owns a cat or a dog? So you see that there's this or here, and there's also a union sign here, right? Probability of A, it didn't really do anything nice. There you go. Nope. Probability of A, I can fix it, but I'm bored now. Probability of A or B equals the probability A plus the probability of B minus the probability of A and B, or the joint probability. This is like a joint probability, the two co-occurring. All we do is add them together. 0.35 plus 0.30, which is 0.65, minus 0.15 equals 0.5. So the probability of owning either a dog or a cat is like 50-50, right? We can test for independence. Is owning a cat independent of owning a dog? That's a good question, and we can actually test for that. We have independence if the probability of A times the probability of B, so it's the product of these two, is equal to the probability of A intersection B. We know we have independence. So let's do that here. We know the probability of A intersection B is 0.15. We see that right here. If we take the probability of A, which is 0.35, and multiply it by the probability of B, which is 0.30, we get 0.105. Well, 0.105 is not equal to 0.15. So this is our joint probability of owning a dog and a cat. So these two are not equal, therefore they are not independent. Which makes sense because people who own one type of pet are probably more likely to own another. Let's talk about conditional probabilities. Conditional probabilities mean that when event A occurs and then event B occurs, event A provides us some information about event B. So it's a condition. We say, what's the probability of event B occurring given, and this line here is the delineation of the condition, which is A. So what's the probability of event B occurring given event A occurred? So that's the condition. So what's the probability of B occurring given A occurred? So by definition, and you can manipulate this equation to do a lot. So this is the probability of B given A is the probability of A intersection B divided by the probability of A. So long as A is greater than, so obviously A can't be 0. Otherwise this would be undefined. So let's go to another pet example here. What is the probability of dog ownership given one owns a cat? Well, we have all this information. probability of dog, this is the intersection of the two, probability of dog and cat occurring. We know that's 0.15. And the probability of cat ownership is 0.35. This is 0.429, or 43%. 43% chance that one owns a dog given one owns a cat. So that they're related, right? They're not independent. The general multiplication rule, like we just did the addition rule, the general multiplication rule, as you can see, is just a rearrangement of this equation. So if I multiply both sides by the probability of A, I'll get the following. Probability of the intersection of A and B is the probability of A times the probability of B given A. We want to know what's the probability that one owns a dog and one owns a cat. Well, we already know that, right? We know it's 0.15. It doesn't take a genius to see that because I already listed it as 0.15. But we're going to make sure we're right. So we take the probability of a cat with ownership, which is 0.35, and multiply it by the probability of owning a dog given one owns a cat, which we know is 0.429, and we get 0.15. So that's a way to verify. This tells you also that there are different ways you can verify your results. You're not always going to have everything that you want, like you may not know this and you might want to calculate it. So you use this multiplication rule. A total probability rule, that's a probability of an event. Like if I want to know what the probability of A is, well, let's see. Probability of A has two pieces. One is this little piece where they intersect, right? So this is the probability of A intersection B, or A and B occurring right here in this little football shape. Plus, it's the probability of this part of A that does not intersect with B. So if we look at this equation, even though it looks funky, it states exactly what I just, or it replicates exactly what I just said. So it's the probability of the intersection A and B, which is this football shape right here, plus the probability of A intersection with not B. I know it sounds weird, not B. So this is B, and the rest of it is not B. That's why you have this section here. So it's where the two intersect. They intersect right here, this moon shape, right? This moon shape. We'll need that in a second. So we'll see how that works out. Let's look at Bayes' theorem. We use Bayes' theorem when we're dealing and for us in epidemiology, when we're dealing with positive predictive value, or when we're calculating positive predictive value. But it's a type of conditional probability. It's a probability of A given that B occurs. It's probability A intersection B divided by the probability of B. So this works out to the probability of B given A divided by the probability A divided by the total probability of B. So this is exactly what we did up here. So it's the probability of B given A times the probability of A. So that's the intersection. So this part and this part are the same. The numerator and the left part of this sum are the same. Plus the probability of B given not A times the probability of not A. We translate this into epidemiology terms. We can calculate the probability of a disease given one tests positive for the disease. You'd think that that's going to be pretty high given one tests positive for the disease, but it's not necessarily, because it depends on a lot of different values. So let's see. The numerator then is the probability of testing positive. So PPV should be, I'm going to write this down here actually. So bear with me for a second as I write this down. So I want you to make sure you get everything. Yes, I don't want you to have anything missing anywhere. And let's see, we need this to be, let's do one of these bad boys right here. Okay, all right, go. Given one tests positive for the disease. I love this little tool in word. There you go. All right. So it's the probability of being disease positive given one test positive. So that translates the probability of testing positive given one's disease positive times the probability of being disease positive divided by the total probability of testing positive, which is, again, probability of being, the total probability of testing positive. You can test positive given your disease positive, or you can test positive given your disease negative. So we need both of those components. The probability of disease positive is what we call the prevalence of the disease. So 1 minus the prevalence would be here, and we'll see that this piece right here, the probability of testing positive given one is disease negative, is what's called a false positive. We translate that to sensitivity times, this is the sensitivity of a test. Sensitivity of a test is the probability of testing positive given one is disease positive. It's not the same. See how PPV is different, or just the opposite of one another. Sensitivity and specificity, as you know from if you took epi, and I know you did, these are properties of a test. So we have sensitivity times prevalence divided by sensitivity times prevalence plus 1 minus the specificity, which is the false positive, and I'll show you again in the table in a second, times 1 minus the prevalence. And here's a nice little contingency table for some kind of disease with a prevalence of 5%. Test sensitivity is 99, test specificity is 0.95. Using the equation, we have the sensitivity is 0.99, you're given that. We need the prevalence, well, it's 5%, but I just want to show you 5% is derived from this equation here, or this quotient here, 500 divided by 10,000, or this proportion, 500 divided by 10,000. Right, it's 5%. So that's your numerator, which is 0.0495, and your denominator is the total probability of testing positive. Right, this is testing positive. You can test positive and be disease positive. That's your sensitivity. Or you can test positive and be disease negative. Now you'll notice that sensitivity, the specificity of a test is the probability of testing negative given one is disease negative. That would be 9025 divided by 9500. The complement of that is testing positive given one is disease negative. So it's 1 minus whatever the specificity is here. The specificity is 0.95, so it's 1 minus 0.95 or 0.05. And that's what we see here. This last component is 1 minus the prevalence. So if the prevalence is 0.05, 1 minus the prevalence is 0.95. So we just add those together and we get 0.51. And you'll notice that that's the same value that we derived if we have all the table values. Now you can use all these table values to derive everything if you have a table, but you don't always have a table. If you have a table, you can say, what's the probability of being disease positive given you test positive? So this column here is testing positive. So 970 individuals tested positive. And the probability of being disease positive is 495, because this is the disease positive column. 495 divided by 97, or which equals 0.51, which is the same as what we got here. And that is a wrap for this little lecture on probabilities. I want to thank everybody. If you have any questions, please feel free to comment. Let me know. Thank you. Bye.